planning research. Often doing pilot testing is the really fun part as you explore and try things and figure out how to run a good study to address your research questions. One of the big questions is, what N do I use? I'll take two approaches, one precision for planning, and here the idea is we ask, what N do I need for this particular design I've chosen so that the confidence interval I get on the result is most likely not too long. Of course, large N will tend to give us shorter confidence intervals, and we've got a trade-off. Run a bigger study, choose a bigger N, and you're likely to get a shorter confidence interval. That's good, but at the price of larger N. Here for a start, N and confidence interval length, if we choose N equal 20, we get reasonably short confidence intervals. N equal 5, a ridiculously small study, and we'll get on average much longer confidence intervals. No surprises there. Now let's look at another aspect of these dances of the confidence intervals. For N equal 20, there will be variation from study to study, of course. So here we've got a rather longer confidence interval, a slightly shorter one, but there's only a moderate amount of variation from study to study. In comparison with this very small sample where there is extreme variation in confidence interval length from study to study. So here's one study with N equal 5 that gave this extraordinarily long confidence interval, and the next one happened, just by sampling variability, to give us a really very much shorter confidence interval. So we need to be conscious of the amount of variation in confidence interval length, the amount of variation in MOE, and how that is different for different sample sizes. But still, the first point is the major one, which is that large N, on average, shorter confidence intervals. We're going to consider the two basic designs, independent groups, and here our effect size of interest is, as usual, the difference between the group means and the confidence interval on that difference. And we're interested in the relationship between N, the size of each group, and MOE for this confidence interval on our effect size. Then in the paired design, once again, we're looking at this effect size, the mean of the paired differences. We're interested in the relation between N, the number of data pairs, and MOE for this confidence interval. There's one additional thing to consider here, and that is rho, the population pre-test, post-test correlation. Now, the larger rho is, the larger the correlation between pre-test and post-test data points is likely to be, and the shorter the confidence interval. When rho is large, then we expect shorter confidence intervals, which is great news. Here are the 4 points to bear in mind. Overall, larger N, smaller MOE. What do you want for your birthday? Large N. Why? Because it gives, on average, more precise answers. For a given sample size, confidence interval length varies. Assuming we don't know population standard deviation. Sigma. Smaller N, confidence interval length varies more. And for the paired design, there's one additional thing to consider, rho, the correlation between the two measures, between pre-test and post-test. And the larger that is, the better the reason we have for using a paired design, the more sensitive an experiment we have, and the shorter is the CI on our effect size. Hooray! So here we are, we're pondering what sample size we should choose, knowing that the bigger the sample size, the shorter the confidence interval we're likely to get. It's not so much a matter of picking what is the correct N, but understanding what the trade-off is in our particular situation. Bigger N, of course, more time, effort and expense, but the payoff is shorter confidence interval. Or perhaps we can't afford such a big N, so we need to accept that we're going to get a longer confidence interval. And if we understand that trade-off, we're in a good position to choose what's a sensible N for our study and to know what precision it's likely to give us. This is the Precision 2 page in ESCI, which we'll use if we want to use two independent groups, each of size n. And basically it's a graph showing us how n varies with MOE for the confidence interval on our effect size, the difference between the two means. And MOE is expressed in units of population standard deviation units. Think of it as the units of Cohen's d. This cursor here is set at 0.4 and tells us two things. Well, we can look at it two ways round. If we have a study with two groups of 50, then on average we're going to get a confidence interval with MOE equals 0.4. Or if we want to set a target MOE of 0.4, then we need to use two groups of size 50. Two groups of size 50 will on average give us MOE of 0.4, but there'll be variation. And here is the sampling distribution of MOE that tells us about that variation. Most likely we'll get MOE round about 0.4, but we could easily get MOE down to 0.35 or up to 0.45, but we'll virtually never get values above 0.5 or below 0.3. Now, if you wanted to target MOE that was smaller, would you need larger samples? Of course you would, down here. Let's change this graph a little. Change the scale. Now if we want target MOE of 0.2 rather than 0.4, we're going to need n of 194. So MOE half as large on average, we're going to need n roughly 4 times as large. That fits with our informal guideline, doesn't it? Before I move this target cursor over, perhaps pause the video and think about this question. Will this sampling distribution of MOE be wider or narrower when we go down to smaller MOE and larger n? Think about that for a moment. Now let me do it. Here we have MOE at 0.2 for n equals 194, and of course much larger n means much less variation from study to study in MOE. Knowing that n equals 50 gives us MOE on average of 0.4 is all very well, but for our particular study we might get a somewhat larger MOE. Can we do better? Yes, by using the concept of assurance. If I click here, then I get a second curve, this red curve, which tells me about what n I need to get MOE with 99% assurance. So I know that if I use two groups of 50, I'm going to get 0.4 on average. Well, now I know that if I use two groups of 65, I'm almost certainly going to get MOE less than 0.4. And here's the sampling distribution with only the tiniest little tail there above 0.4. In fact, 1% of the area under this sampling distribution is above 0.4. So n equals 65, and I'll be 99% assured that the MOE I'll obtain will be less than 0.4. In fact, most likely it'll be around about 0.35. Now let's turn to the paired design. And on this second ESCI page, I have the same sort of relationship for the paired design. A single group of size n and paired data. So again, I've got target MOE. I've got a sampling distribution for MOE for a paired design with n equals 14. But remember, there's one additional thing I have to specify, the correlation between the pre-test and post-test between the two measures. Here it's set by this slider, and here I've set rho equals 0.7, which is a typical fairly high value. And this tells me that a single group of only size 14, how wonderful, how luxurious, will give me on average MOE of 0.45. Let's increase my rho up to say 0.9. What's going to happen to this curve? Will I need larger n or smaller n? Think about that for a moment. Let's try it. Yes, a smaller n will do if we've got a more sensitive experiment because rho is larger. And if we go down here to assuming more conservatively just a smaller rho, say 0.6, then we need a larger n to give us our MOE of 0.45. Again, we can use assurance, and this tells us that a group of 18 will on average give us MOE of 0.45, but if we have a group of 29, considerably more, then we're almost certainly going to get MOE less than 0.45. And as before, if we move our target MOE down, maybe MOE of 0.3, then n equals 54 will give us, with 99% assurance, MOE of 0.3. So by playing around with these sliders and these values and thinking about what these sample sizes mean and what MOE means in our situation, and very likely we'll once again arrive at the conclusion that the paired design is usually better, more sensitive if it's appropriate. If we have even just a moderate sort of value of correlation, rho of 0.6, then moderately small samples will give us quite reasonable MOE, compared at least with the independent group's design. Now, precision for planning is terrific because it brings great coherence to what we do. We're thinking about effect sizes and especially MOE at the planning stage while we're conducting our study, while we're analysing, and we make our interpretations afterwards in terms of effect sizes and confidence intervals. So a MOE is critically important, and that's exactly what we put into any meta-analysis. So enjoy precision for planning.